There we go. I forgot that sometimes. So the webcam has a microphone built into it as well, and I have that one muted because I have this guy, which is a much better microphone. But when I plug in the webcam, sometimes it switches my default mic for some reason. So hopefully you guys can hear me now. So in that case, I'll start over some of my spiel. Hey, I'm David. I'm David Watley. I am the membership director for the Northeast Florida Astronomical Society. And uh, here on the NEFAS page, this is nefas.org. I was just talking about how if you want to become a member of NEFAS, if you live in Jacksonville or the greater Jacksonville area, want to be a part of what we do, you could always go right here to membership, join NEFAS. That's nefas.org, nefas.org. And I'm going to put that in the group chat for anybody interested in joining our club. I am also a member, not on the board, but a member of the Ancient City Astronomy Club, which is our friends down in the St. Augustine area. So if you live in the St. Augustine area, check them out as well. I'm going to go ahead and post their address as well for you guys. And paste that right there. So that's the St. Augustine guys, the Ancient City Astronomy Club, another great group of guys, and they are very passionate about space and the universe. Two great astronomical communities. If you live in this part of town, honestly, you can't go wrong joining both of them. I'm a member of both of them. But if you only join one club, NEFAS is the Jacksonville Club, and Ancient City is the St. Augustine Club. And I highly encourage becoming a member of an astronomy club if you are interested in astronomy, if you're thinking about buying a telescope or you have a telescope, any of that kind of stuff. Being a part of an astronomy club is the best way to get out and start doing it, actually start doing astronomy and learn from other people. But tonight is about learning through the form of a virtual planetarium presentation, which you don't need a telescope. I will be your telescope. And we can just go ahead and get started. One other thing I'm going to say again, because I was on mute earlier when I was saying this show is not for me. This is not to give me a platform to feed my ego by talking all day because you guys are listening to me. This is to give you guys an opportunity to ask your questions and learn the things you've always wanted to learn. In that regard, also, I think it's wonderful that a lot of the club members like to come in and participate in these, and obviously that's awesome. But this is also meant for people who are not a member of an astronomy club or have an astronomical knowledge and are brand new and may have questions about all kinds of things. So definitely share this presentation. Share it now. It's ongoing. We'll be going until 8:30. You don't have to be here from the beginning. So share it with people you think would be interested. My goal is just to get this stuff out there and let people learn and answer people's questions about everything from stars to comets to galaxies, whatever it is you're interested in learning about. My policy is always that there are no stupid questions. So sometimes, and kids are great about this. I've never have a problem with kids. Whenever we do presentations and there's children at our public observing events, they're the best. They ask every question that just pops into their little heads. They're not scared to ask anything, and they ask some of the most interesting questions and really are great for participation. Adults are the ones, excuse me, my blood pressure medication makes me cough, so adults are the ones that you're always having to like convince them to be comfortable asking their questions, right? Somewhere between childhood and adulthood, somebody convinces us that there's this thing called a stupid question and that you don't want to ask a stupid question. You don't want to reveal that you don't know something. But the whole point of a question is that you don't know something, right? The whole point is that you go from a place where you don't know to a place where you do know. So if there's something that you don't know that you would like to know and you ask a question, it is by definition not a stupid question. Right? Any question honestly asked is a good question. And oftentimes the ones that people are afraid are like really obvious stuff often are really interesting. Things like what is a comet, for example, is actually a really interesting question. And a lot of people think they know what a comet is until they ask, and then it turns out that there's more to it. So stuff like that. So I just wanted to encourage everybody, like I said, that there's no such thing as a dumb question. Ask away, ask whatever questions you have. The chat is ongoing, and I'll be checking that continually throughout the presentation. Again, it looks like we have 3 people. If you're here, say hi in the chat. When I'm doing these presentations, I'm just talking out of camera, and I'm used to doing these in public in a big crowd. So if you guys are saying hi in the chat, even if it's not a question, you're just saying hi, you're just participating, you're just getting the conversation going, that helps me not feel so alone in the universe. That feedback is really helpful. It kind of gives me the energy to keep going. So I like seeing that activity in the chat. So don't be shy. Say hi. Let me know who you are. Let me know you're here. Right? I want this to not just be a lecture. I want this to be a conversation. Right? This is a discussion. This is a conversation. And it's about you guys. You guys are going to be the determining factor here. Right? You're the director. You're the script writer, not me for this presentation. That said, I don't have any questions in the chat, and I have been thinking since the last presentation about a couple of topics I could talk about while I wait for questions. So I'm happy to do that. But again, don't just passively observe. Get in there, ask your questions, or bring up topics you're interested in. Or as I'm talking, if something catches your fancy, definitely hop on that. I know sometimes if you're just put on the spot and said, okay, ask a question, maybe you don't know what to ask. But as we're going, anything that occurs to you, just throw it right in there. So this right here, I'll start off. This is Stellarium Web. This is free planetarium software. It's available online. You don't have to download anything. It just operates right there in your web browser. And that's what I use for my presentation. So you can actually pull this up yourself. You can find these things yourself. And this is what I use to talk about the universe when I do my presentations. And one of the things that Stellarium does when you first fire it up is if it's not already nighttime, it will fast forward a little bit to be nighttime, and you can tell it where you live. So I've got mine set for near Jacksonville, right? So this is the sky that we would have tonight at 10 o'clock, right? 2200, that's 10 o'clock in military time, right? So this is our 10 o'clock tonight sky, 10 p.m. So if we don't have any clouds or anything, this is what you would see. Of course, in Jacksonville, because of light pollution, we wouldn't see quite this many stars. But one thing I'll point out about the Stellarium software that I use is that the size of the dot correlates directly to the brightness of the star, right? So visually, the stars do not appear as circles or dots. They are all pinpoints, right, visually. This software uses size as a stand-in for brightness, which is typical for astronomical charts. So if you look at what some of these brighter dots are, these big dots are the ones that we would tend to see even here in Jacksonville. Now, right now it's May 20th, and so we are moving into the summertime, right? We're kind of getting out of spring and approaching summer, and so we're going to start to have more springtime and summertime constellations, and we're going to be saying goodbye to our wintertime friends. So if we look here to the west at 10 o'clock at sundown, you see Capella and Castor and Pollux here in Gemini, Procyon and Canis Major. Capella, by the way, in Auriga, that's that constellation. These guys are already on the western horizon. They're going away. If I speed up time, right, if I just advance time like this, you see we're going to lose those. If I rewind time a little bit by rewinding months at a time, I can bring them back. These are some of the constellations we associate with the winter: Orion, Taurus, and all that. But right now, those guys are going away. Bring it back to tonight at 10:16. And we're going to start to get some of the springtime and wintertime constellations. So let's talk a little bit about what is in the sky tonight. So if you're new to finding constellations, it can help to try and find something very easy and familiar, something that you can easily recognize with little difficulty, and then we can use those to help us find additional constellations. So again, man, it looks like we've only got 1 or 2 people in the stream. Is there not anybody else? Again, if you're here, say hi so I know you're here, because according to YouTube, I've got 2 people watching, and again, I might be one of them. But I'll just keep talking. So So the easiest way is to try and find some kind of a familiar landmark constellation. A good way to start is we can try looking to the north, right, to try and find the Big and Little Dipper. They're not always going to be easy to find. Sometimes the Big Dipper especially might be below the horizon, but if we look up, there it is, right, and we find these 7 stars of the Big Dipper. And if I add in the lines, there we go. Now, the Big Dipper, interestingly enough, not technically a constellation. The Big Dipper is actually something we call an asterism. And what that means is that there are 88 officially recognized constellations. They are officially recognized by the International Astronomical Union as constellations. The Big Dipper is not actually one of them. But what the Big Dipper is it's a recognizable pattern of stars that's not one of the 88. It's actually part of a larger constellation that is a true constellation called Ursa Major. Bearing in mind, of course, that these are all just things that somebody made up. Somebody decided that this is a constellation and this isn't, but that's how we categorize them. So Ursa Major is the Big Bear, and as you can see, there's a whole body, there's a head, front legs, hind legs, and a big tail. If I add the artwork, you can kind of see the bear there. But the Dipper is all particularly bright stars. You see these are all nice big dots here in the Stellarium program. So if you're new to finding constellations and you're trying to find something, start off by seeing if you can find the Dipper. And if you can figure out which direction is north, that's the way you should go. Because if I zoom out a little bit and I do a bit of time travel here, you'll see that the Big Dipper, however far it moves, it's always more or less in the northern part of the sky. And we can usually see it from about, it starts to appear in December, January, and it hangs out with us until about September and starts to hit the horizon around October. So it's usually there for most of the year. It's a pretty reliable constellation. And then I'm going to show you some tricks to find several other constellations using the Big Dipper as your guide. So, for one thing, I actually want to quickly take an aside and mention something just because this was something that was kind of cool and I thought I'd bring it up for you guys. One of our club members is from India, and we were out at our observing location, the swamp, the other night. We call it the swamp. And we were talking about the stars, and I just asked him, I was like, do any of these constellations have different meanings or different stories behind them in India than what we have here in the West, right? Because I know that is the Big Dipper. In the UK, they call it the plow. You know, is there anything interesting that you could tell me about it in India? And so he told me that in India, these 7 stars represent 7 sages, 7 wise sages, and that this star, Mizar, if you look, there's a second star right by it. And I'm going to try and remember the name he told me. He said that this, I forget the sage's name, but I remember he said Arundhati was the name of the wife, right? That this is actually his wife is what that star represents. And so he was saying, and of course traditions may differ locally. I'm just repeating what he was telling me, that at weddings in India, oftentimes there's a part where they'll stop and they'll look because they're looking for this pair of stars. And I thought that was kind of cool. I thought it was interesting that that's a part of the wedding tradition. And so he was explaining that to me. I thought, man, that's really cool. I should bring that up next time I do one of my presentations. So that's a neat little story about the Big Dipper. But once you find the Big Dipper, we can use that, like I was saying, to find several other constellations. So one thing we're going to do is we're going to take the curve of this tail. I'm going to zoom out a little bit. And the rule here is you can arc to Arcturus. So we draw the arc to the next bright star, right? We take that curve around, and we hit this star right here, which is called Arcturus. Now, Arcturus is a part of a constellation called Boötes. And I'm always a little iffy on if I'm saying it right, but I'm pretty sure that's how you say it. And Boötes is kind of hard to see in this program, but if you look, you'll see that there's sort of like this diamond-ish pattern, like a long, almost like a necktie shape, right, of bright stars. And then there's these stars here, and then there's like a couple of stars out here. Personally, I've always, if I add the lines, you can really see it. I've always felt like this kind of looks like the fish, like you see people put on the back of their car, right, the Christian fish. or like a necktie, right? Booties is, and this one doesn't show, but usually the second O has the dots, which is why I'm saying it like that, booties. This one is a shepherd, apparently. It's supposed to represent a shepherd. Once you find that one, there's a second star you can do. So you can arc to Arcturus, and then you spike on, meaning you continue on to Spica, right? Now, this view zoomed out like this, it's really distorting things as you see. In the actual night sky, this line appears more straight, right? So you come down to Arcturus and then you shoot over to Spica. And Spica is actually one of the stars in the constellation Virgo. So Virgo is a definite springtime, summertime constellation. I'm going to add the lines again so you can see there's this sort of box shape here of these bright stars. And then this is sort of the body, and then we have one arm here, one arm reaching up here. At least this is how I see it. And then her two legs are kind of coming down, and she's just sort of like reclined, like maybe she just fainted on her fainting couch, right? Like back in the Victorian age. Let's see here. Okay. Chester wants to know more about joining Nephis. Yeah, okay. So I'm going to hide this message actually because it contains personal information. Becky, thank you for the tip. If you want to privately message me that, I'll take it. I'm hesitant having someone's phone number live on YouTube, so I'm not going to reveal your comment. I'm going to keep it hidden for that. But that's awesome. He wants to join Nephis. That link I put in the chat, you can feel free to share that with him. Text him that. And also my own email address, which I'm happy to put in the chat because this is my Nephis email. This is just for emailing me stuff about the thing. It's membership@nephis.org, and he can also email me if he has any questions about joining the club. So excellent. So where was I? Yes, Virgo. So this is Virgo. And then from Virgo, another one we could find is Leo. Now, there's a couple of good ways we could find Leo. For one, if you find Castor and Pollux, and you look sort of up and to the left from them, that's one way. Another way to find Leo is if we go back to our Big Dipper, and we imagine that our dipper is full of water or milk, apparently traditionally it's milk, and you poke a hole in the bottom of it, it would drain onto the back of Leo. It would drain onto the lion's back and get him soaking wet. So those are a couple ways we can find Leo based on nearby constellations. So Virgo, if I add the lines back in, Virgo is reaching up towards Leo. Or if we poke a hole in the Dipper leaks onto Leo's back. Leo is also near Castor and Pollux. There's a couple different ways to find it. Leo is one of my favorite constellations because many constellations are very much up for interpretation, but I feel like Leo looks like what it is. It's one of those constellations that really does let you connect the dots and you get the picture of what it is. So the brightest star in Leo is this one right here called Regulus. When we find Regulus, we can easily find this sickle shape here, right? This sort of backwards question mark shape. And what this is this is the lion's mane, right? And then we drop back from there. There's this big box. This big box represents the body of the lion. And then Denebula is the tail of the lion, right? So if we imagine our lion, so the artwork is going to differ from you here and show him running like this. I've always imagined him lying down because I don't see any legs here, right? I've always pictured him, he's like lying down. You know how lions, they spend most of their day being lazy. That's kind of how I see Leo. But nonetheless, I really get a feel of this is a lion's mane, right? I think Leo is one of the coolest constellations because it looks a lot like what it is. A good example of a constellation that's a bit more abstract is Corvus, which if we find Spica, you can usually find Corvus. You see there's a fairly bright stars here that form this sort of baseball diamond shape. In this case, this is less connect the dots, more like each star represents a whole body part. So Algorab is one wing, Minkar is another wing, Guiana is the tail feathers, and Kraz is the tip of the beak, right? And so there's the crow is here. Corvus is a crow, right? Now, one really cool thing about this time of year, I'm going to check our chat and see if we've got any questions. Yeah, no, you're good. You're good. Oh, and we have more viewers now. Excellent. The viewership has gone up. It seems like more people have realized the show is starting and they're starting to trickle in. Glad to have you guys. Real quick, I'm going to remind everybody that this is a discussion. This is a question-driven thing. So even though I'm just sort of talking about my own stuff right now, I actually greatly prefer to talk about what you guys want to talk about. So any questions that occur to you, anything you've ever always wanted to know, or if I'm in the middle of talking about something and a question occurs to you, by all means participate in the chat. Even if you don't have a question, just say hi in the chat. Just saying hi, just let me know you're here, helps me tremendously because I'm used to doing these in person and having live human interaction. And right now I'm just talking at a camera in my room. So if you guys are saying hi and you're joking with me and interacting with me, I don't feel quite as alone when I'm doing these presentations. That really helps me to know that you're here. I'm watching, YouTube is giving me a number of viewership, but if you guys are actually saying hi, hey Dave, it's Andrew. Awesome. Good to see you here. So I'll see you Sunday, by the way. We're going to have a lot of food. It's going to be awesome. My birthday's on Sunday, for what it's worth. So that's why I said that. So yeah, definitely helps me to see that you guys are here. And again, I'll reiterate, I don't believe that there's any such thing as a dumb question. If there is a thing you don't know and you would like to know, and you ask a question, by definition, that is not a dumb question. By definition, any question honestly asked is a good question. Children know this. Somewhere along the road to adulthood, we forget it. And so I want you to be like a child and ask whatever question pops into your head. It's not a dumb question. It's a good question because you want to know. You want to learn. So getting back to the discussion, we're talking a little bit about some of these springtime, early summer constellations. If you guys have attended some of my shows in the past, I love to talk about Orion and Gemini when I do the constellation part. Those constellations have set. We have a new set of constellations now that we're looking at. And this is one of the fun things about astronomy is that if you look at the stars, even if you don't have a telescope and all you do is you just look at the constellations and you learn them to be able to look up and appreciate them, one of the cool things you get to enjoy is you get new constellations that creep in and old constellations that leave, and the sky will change throughout the year. It's really cool. Now, one topic I will address real fast is that right now we are full swing in what I like to call, and what many of us like to call, galaxy season. Right? Springtime is galaxy season. If I have my deep sky objects turned on, if I just zoom in a little bit here. Okay, so the web-based version is really sparse, but even now you can already start to see all these little circles. Every one of these is a galaxy, right? I zoom in a little bit more. There's more and more and more and more. Look at all these galaxies. Just look at all of this, right? Absolutely outrageous. This is something really cool. I think this is this over here? Yeah, I think over here we've got Markarian's chain, which is a big chain of galaxies over here. I've looked at this through my telescope, and we're talking not, long exposure photography, just me putting my eyeball, and I sketched. I had 11 galaxies in one view that I could see with my eye. There's more there if you take long exposure. If we look over, so this is that region between Virgo and Leo. If we look over in Leo, we just zoom into this little area here in the tail, we suddenly find all these galaxies here as well. About halfway between these two stars, we zoom in. There's this right here, the famous Leo triplet, but then there's this guy. And if we just move along down the body, there are more and more and more. These are all galaxies. So why is it that there are so many galaxies in this piece of sky, right? Oh, hey, Prasanna's here. He's the guy I was talking about. Prasanna, good to see you in the chat. I was telling them what you were telling me about the Big Dipper and Arundhati, I think you said her name was, the wife of the sage, and how people will look for those two stars. So now you're here participating in the chat. Awesome. Good to see you tonight. So Andrew asks about Bortle levels and how much it actually affects visual astronomy and astrophotography. So Bortle levels are a measurement we use to measure the brightness of the sky. And so I'm just going to wrap up my thought real fast about galaxy season. Actually, no, I'm going to address the Bortle thing real fast. I'll come back to the galaxy thing because I can answer the Bortle one a bit more quickly. So if I bring up the Bortle scale here on our handy dandy Wikipedia and I bring it up for you guys. So, oh, we got to adjust this so you guys can see it. Here we go. So the Bortle scale measures the darkness of the sky, right? And so we have Bortle class 1 is a perfect, excellent sky. This is like after the apocalypse when mankind is long since gone. Or if you go out in the middle of the ocean or in the middle of the Sahara Desert, right, you're going to get a Bortle 1 sky. 2 is truly dark. 3 is more like a rural sky. 4 is more suburban. 5, 6 is a bright suburban, and then we get all the way up to 9. And personally, I think Jacksonville's a 10. Jacksonville is just terrible in terms of brightness. But this is the scale, and this is how we measure how dark the sky is. They actually sell Bortle meters that you can actually take out. I think there's even an app you can get for your phone where you can just take it out and it'll say, oh, it's a Bortle 2 or Bortle whatever. The effect that this has on observing is this. If I can bring back the Stellarium software. So when we think of stars, we typically think that these are bright objects, and they are bright. If you were to go and be next to one, it's daylight, right? It's the sun is a star. These are suns. But at the distance that we observe them, so many light years away, their light has faded considerably. And they appear as bright lights at night, but only because they are against a dark black background. The reality is that these are actually very dim. Most of them. Some of them are brighter, obviously, and they're represented by these bigger circles. Now, whenever we shine any kind of light, whether it's artificial light, or you have a campfire, or even the light of the moon itself, any of this light is going to scatter and bounce and refract through the atmosphere. And so it's going to create a sort of glow over your head. And what that's going to do is it's going to take a pitch black default background of like the black void of space, right? If you're looking away from the sun at the nighttime part of the earth, and it's going to raise that up to a gray color, right? And actually it's not even gray. Sometimes it looks orange because a lot of halogen lights have orange in them. Of course, now a lot of places are switching more to LED lights that are pure white, but so the sky glow is actually changing colors. It used to be more orange than it is now, but nonetheless, we'll just simplify and say gray. And so, if you have pitch black, then any stars that are brighter than that pitch black color are visible. But if you raise the background color up to like a charcoal gray, right? Now, only stars that are brighter than charcoal gray show. And when you look at individual stars, you think, well, that star's white, right? That's got to be brighter. But really, and it is hard to imagine them this way because when we see them against the dark background, they really are that dim. Many of them really would be like charcoal gray if you smeared them across the whole sky, right? If you spread them out. And so when we raise the brightness of the background, the stars can't stand out against them. Now, a telescope helps you to gather light, right? So the aperture of the telescope is like a bucket that we use to catch light coming in from outer space. You can either have a bigger bucket, which is what you need for visual observing. If you're doing eye to the eyepiece, the bigger the aperture of your telescope, the more light you can gather because your eye gathers light sort of live in real time. Or you can gather for longer, right? If we imagine you're trying to collect rain, you can either have a bigger rain bucket or you can leave your bucket out longer to gather more rain, right? So for photography, you can do longer exposure. But in either case, you're going to collect not just the light that you want to see, but the light that you don't want to see, right? And so let me see if I can pull up example images here. to show you. The big problem isn't even just seeing the object. It's being able to pick out the object from the background, right? So a lot of if you're doing visual observing, especially if you're doing deep sky stuff, where you're looking at distant galaxies, nebulae, star clusters, those objects are very faint. They're not very bright. And we need the telescope to gather the light just to be able to see them. But if the background is brighter than that object, you don't see it, right? And so sometimes you'll see the object, but there'll be a lack of contrast between that object and the background, right? It won't stand out. It won't pop. It'll be sort of blended into the background. When you do photography, when you take a long exposure, that helps because you're giving that data, you're giving your chip more data to work with to pick out that object, but you're still going to also get extra exposure of the sky glow. And so your photographs are still not going to look as good. So generally speaking, for any kind of deep sky astronomy, if you're trying to do serious astronomical work, looks like we're having an issue with the stream. Hopefully you guys aren't losing the stream quality here. If you're trying to do any serious astronomical work, then you're going to want to get to at least a Bortle 3, right? The lower the number, the better. So Bortle 3, 2, 1 sky is ideal. Maybe Bortle 4 if that's what you have to work with. In our club, we have a spot out in the Osceola State Forest, which is, I think, a Bortle 2, which is pretty good. And our friends in St. Augustine have a place they go at the fairgrounds, which Andrew, who asked the question, I know you've been to the fairgrounds. We went there together. That's more like a Bortle 3, the sky that they have. So definitely, okay, the stream is good for you guys. So it's telling me that it's not receiving enough data to get a smooth stream. But I guess if you guys say that the stream looks good, I'll trust your it's telling me poor stream health. But if you guys say it's good, then I'll keep going. So yeah, you want to get out under a dark sky, and this is why, if I can hop on my soapbox real fast, while I'm talking to the 4 people who are here, this is why we rally so much against light pollution, right? And the solution, we're not trying to say we're going to take away everybody's lights, right? So I know it's a hard sell to say like, hey, no more street lights, no more house lights, turn off the lights in your car. Right, light pollution bad, and people are like, well, we have to have a civilization, right? I get that. What we really want is to meet us halfway, right? And this is really a message for businesses or for people who want to start doing like a letter writing campaign to whoever or encourage local businesses. There's no reason to shine light upwards, right? So if you've got lights in the parking lot of Walmart, for example, those lights can be constructed in such a way that they're shielded above and the light is just going down, right? Now, there's going to be some bounce off the pavement. It's not perfect for light pollution, but it's better, right? And it's actually more efficient because you're getting more use out of that light, right? Any light you shine up is light you're paying for that's not doing any good. It's actually cost savings involved. When you build more efficient lights, they function better. You get more out of fewer lights, right? Backyard lights on your house, right? Try to get ones that are shielded, that shine down. We don't want to just have stuff throwing light sideways and up because that's going to just get added to the atmosphere and contribute to all this light pollution. We got a follow-up question about filters. So follow-up question, looking at astrophotography photos, you see colors based on filters bringing out the hydrogen, sulfur, and oxygen, like the Hubble shots. Do these colors actually exist to the naked eye? The answer is kind of. The answer is actually complex. This is a really good example of what I'm talking about, how when you ask a question, even one that you're worried may be kind of a simple question, or to use a word I don't like to say, a dumb question, which is definitely not, but how the answer may actually be more complex and interesting than you may have thought. The answer to this is actually really complex and interesting. I'm going to bring up an example of what we're talking about, the classic pillars of creation. Nebula is a really good example. So a lot of times when you see images of this stuff in space, you see these amazing colors, right? And especially when you see like Hubble stuff, right? You see these amazing colors, and the question is, can you see these with your eyes, right? Are the colors really there? Are they really available to your eye, or are you never going to see these? And the answer is sort of. So for some of this stuff, the color truly is there. The Orion Nebula really does have a greenish tint to it, or on long exposure, it's really purplish. Even if you don't do any kind of weird, crazy post processing on the color, if you just sit and take a long exposure of the Orion Nebula, it looks purple, right? If you do that with the Heart Nebula or the Soul Nebula, they look red, right? Horsehead looks red. Red and pink are really common colors. Now, this image and similar ones from the Hubble are what are called false color images, meaning that they use spectroscopy, where they break apart the spectrum of the light and they look for specific lines associated with certain chemical elements, and then they dye the image sort of to represent the presence of those elements. So they'll say there's a lot of oxygen, so they'll make that part of the image a bit bluer so that the image conveys some data visually, right? Where you can see there's hydrogen or there's oxygen or whatever in the image. And so there is such a thing as a false color image. Also, there are many images that are taken not in the visual spectrum at all, like X-ray images, right? If I pull up, we'll do the Helix Nebula is usually pretty good for this. So the Helix Nebula, now even with just a long exposure photo, these colors are really there. This isn't 100% false color. This thing actually is colorful. But this image of it right here, right? This is actually in a different wavelength of light. This is in the infrared. Oh, and this website's cool. It's got a slider. Okay, so infrared, visual spectrum, ultraviolet, right? X-ray. You see there's just points here. And in fact, the object itself is not emitting X-rays. It's transparent to them. You're seeing stuff behind it. And then this is sort of like a combined hybrid of the different wavelengths. So some of the images are not even showing you visual spectrum data. They're showing you things outside the visible spectrum, such as this really cool looking infrared that you sometimes see if you search that. Now, that said, there is color in a lot of these objects. They are emitting light in different wavelengths, and different wavelengths are associated with color. But there's another component to why you're not going to see it through the eyepiece of your telescope. And that actually has to do with the design of the human eye. So if I bring up a map of the retina, rods and cones map. Do I have one that shows the whole retina? That's all right. We'll just use this guy up here, as I've used it before. All right, so this right here is, and again, now's a great time to remind everybody, I don't own any of these pictures, and I don't monetize this video. This is just for educational purposes, just to learn. No one's making any money off of this, so if you own this picture, please don't come after me, man. I'm just some guy trying to educate people on science. So I'm just going to have to leave it up here in the corner right now. But this is showing you the distribution of rods and cones on the human retina. And basically, you have rods and you have the cones. Rod cells only detect the presence of light. They don't know what color it is. But what a rod cell can do is it can tell you how bright the color is. So the more that rod is activated, the more that rod responds to light, the brighter that light, and the less it reacts, the dimmer. Now, rod cells are only sensitive to a certain portion of the spectrum, right? And so they only see certain things, but they're good at seeing faint light, right? They're better at it than our cones. Our cone cells can tell what color the light is because we have different cones sensitive to different parts of the wavelength, and the different amounts that they're activated tells you the color. So when you see a red object, it's because your red and your green cone, which actually overlap a bit, are being activated, the red more than the green, and so you can see that it's red, right? If an object is yellow, that means they're being activated more evenly, and so on and so on. It happens to be that your cones are not as sensitive as your rods. So, unfortunately, many of the objects we view through a telescope, even with the assistance of a big aperture and a lot of light gathering power, are so dim that only your rods can pick them up. And so only your rods actually see them. And so for many of these objects, when you look at them visually, even though they are colorful and that color is really in the object, and that data is coming to your eye, that light is reaching you, and it has the spectrum. It's not just in the white part of the spectrum. That light is so faint that your rods can't differentiate the color, and your cones don't notice. And so when you look visually, most deep sky objects, most galaxies, nebulae, things that Angie's talking about, most of those objects are going to be too faint for your eye to actually discern color. But it gets even worse than that, actually, because different wavelengths of light are actually different levels of energy in terms of basically shorter wavelengths are more energetic, right? So blue light is more energetic than red light just because of the fact that it has a shorter wavelength, right? This is why when a poster that you leave outside, it fades, it always turns blue. That's because the red ink has to absorb the really high energy blue light, and that energy destroys the ink over time, whereas the blue ink can reflect the really high energy blue stuff and last longer. So it happens to be that our rod cells don't know one color from another, but red light activates them less than yellow or blue. So the redder the object is, even though it's going to look gray to you, the redder the object itself is, that is so faint, the harder it is for your rods to see it, because red light just doesn't register as strongly when it's really dim like that. This is why astronomers actually use really dull red lights to read our charts at night, because your rods detecting the light are what sends the signal to open your pupils and switch to using your cones and go to like daylight mode, right? So by using red lights, we can avoid that, right? Because our cones see them, but the rods don't, and we can read our charts. But for some of these distant objects, if they're particularly red, your rods have a difficult time seeing that color. And so they will appear even more faint. So a really good example of this, and I'm going to turn my visual aids back on again, is the Horsehead Nebula. All right, so I'm going to bring this up. Horsehead Nebula. Anybody who's ever looked at this thing through a telescope can tell you that it is basically invisible. It is incredibly, incredibly dim when you're looking at it visually. And you can see how red it is, right? This is not a false color image. This is the real color. Now, this blue guy down here, not hard. Every time I've tried to see the Horsehead, I always see that blue guy instantly. But the Horsehead, and it just looks like a blurry star. Yeah, there's a star in the middle of it. Kind of looks like a blurry star. But the Horsehead part, always really, really, really faint. This glow behind the classic silhouette of the Horsehead. And that's because even though, in terms of actual brightness, the Horsehead Nebula has a lens brightness number of 1, which is the brightest rating. And there are lens brightness 2 objects that you can see visually through a telescope. Nonetheless, because this object is so red, it's especially difficult to see. You have to use special filters and patience and get out under like a Bortle 2 or 1 and have a really big telescope. And even then, it's hard. I've described it as, imagine that you are looking at something that is the color of asphalt at midnight, and you're looking for a hole in the asphalt. And that asphalt is against a background that is the dark void of oblivion. And you're seeing it with your imagination, right? Like, it really is that difficult to see this visually because it is red. But even though your rod cells won't differentiate the color, we can actually still use the color to help us see things, because there is something called a filter, right? An astronomical filter, a nebula filter. Passband. I'm getting a little far afield now, I know, but I think the people who are watching are interested in this topic. So these guys right here only emit certain colors of light, certain wavelengths of light to get through them. Everything else is bounced back out. And we can break that up on a chart like this. These numbers here are the wavelengths of light, where these longer wavelengths are more red, and these shorter wavelengths are more blue and violet. And right here in this 500 range is sort of like a teal color. And this is the color associated with ionized oxygen, oxygen that has been ionized twice in a vacuum, right? It has to be in a vacuum to produce this. And you see this curve shows what the filter allows to get through. So it lets this get through, and it lets some of the stuff down here at the red, which is associated with things like the Horsehead Nebula. Everything else gets blocked. And so what this does is it doesn't make your object any brighter. But what it will do is it'll make the background darker so that the object is easier to see. So even though with some of these things your rod cell won't see that it's teal, just cutting out everything that isn't teal will still make it so that that bit of light that your rods interpret as a shade of gray is easier to see. This picture is a really good example of what I'm talking about, actually. And credit to whoever took this picture. This is a good example of both effects. Right, so this is, I'm going to scroll down here. This whole article, by the way, is really fascinating. I've read through this before. I'll post it for you guys and give credit where credit is due. It's everything you've ever wanted to know about filters and how they work. Credit to the Prairie Astronomy Club. You guys rock. Yeah, props in the I looked at the Horsehead through Chris's 18-inch telescope. And so we're talking 18 inches of aperture, proper filtration out at the swamp. And it was still, man, it was tough. It was tough. So here you see, this is what a light polluted sky would look like, or a, whatever. And then after filtration, or if you get somewhere dark, you see how the object itself is no brighter in this image than it is over here. But because everything else is darker, it stands out. That's the effect of filtration, right? Now, this right here, this teal, this really is what it looks like. Some objects are bright enough that your eye can see color, and the Orion Nebula is a good example of that. It looks greenish even without a filter. And then you throw the O3 filter on where you're saying you're going to only let that teal shaded light get through, then it really looks teal, right? And the contrast improves dramatically with that filtration. But filters aren't magic. And a filter is only going to be able to do so much, right? Because as you saw, those filters in those pictures were not like, it's not like you look at the filter and you see a reflection of your face. They're not that selective, right? They do let some light of all spectrum get through, and it's just dimmer. And so bad light pollution still powers right through those filters. So you still want to make sure you're getting somewhere dark when you're using them. And if you are into visual astronomy and you're thinking about buying a filter, I'm going to put it in the chat. Your first filter, if you only can buy one, you can only buy one filter, buy a UHC. It's an ultra high contrast filter. That's going to be your best bang for your buck. It's going to work on the most number of objects. And it's very aggressive at cutting out the light pollution. They sell broad passband filters, but in my opinion, you might as well not use a filter. Like if you're going to use a filter, go for it, right? Really filter. The unfortunate thing is when we're using a filter, we're selecting for particular wavelengths of light. Nebulae glow in particular parts of the spectrum based on the gases that they're made out of, but stars are white for the most part. They glow white. Some of them are a little bit redder or whatever, but they mostly glow everywhere. And galaxies, that aggregate of all those stars, are basically white. So whereas a filter can say, cut out everything that's not this nebula, galaxies glow in too wide of a portion of the spectrum to be able to select for them in this way. And so if you use any kind of a filter on a galaxy, you just make it worse, for the most part. Sometimes it can help a little, but for the most part, you can't really filter for galaxies, but you can filter for nebulae. If you have a bit more money and you want to get a couple more filters, I highly recommend the O3 filter, which is spelled like that, letter O, Roman numeral 3. That one is basically like the ultra high contrast, but it also cuts out the red part. There's not a huge difference between the two. They're very similar. Side-by-side tests will reveal the difference. Generally speaking, the UHC is really good for improving contrast between the object and the background, and is a less aggressive choice and works a little bit better in like a Boreal 4, Boreal 5, light polluted, like suburban kind of sky. In O3, is a more aggressive filter, and it works on a narrower class of objects. So some objects, especially redder ones, are lost completely with the O3. But the other thing is that they often will increase fine detail contrast within the object. So if you want to buy two filters, then get both and experiment from object to object. If you're only going to buy one, UHC is probably your best bet. And then if you just have way more money than sense, hydrogen alpha. Or is it beta? I always forget if it's alpha or beta. One's for photography, one's for visual. I'll have to check it again. And then that's, like I said, more money than sense because you spent like $100 on a filter to see 5 things. Of course, this is the part where I admit that I have one. And it's absolutely required for the horse head. Everyone jokes that you buy that filter to look at the horse head to use it for nothing else. There's like 5 or 6. There's more than that, but it seems that way. There's a handful of objects that use that filter. And then color filters are a different thing entirely. And then astrophotography uses a whole different thing entirely as well. So that's a pretty in-depth discussion on light pollution and the color of these objects. But when I put a filter on, for example, and I show somebody the Orion Nebula and it dyes everything green, people sometimes say, like, is that really the color or is it the filter? And the answer is kind of yes to both, because yes, it is the filter making it look greener than it normally would, or look more teal because it's being, like, because we're discriminating for just that color. But that color is there because the filter didn't add any color that isn't already there. It just cut out some stuff. So the object really is putting out that color, which is why otherwise the filter wouldn't work, right? So excellent question. Very interesting question about the colors of these objects and what they can tell us. And actually, I'm going to keep going on this color question unless anybody else has another question, because this touches on so many things. And this is what I was saying before about how I like to use you guys as a jumping off point. I'm going to pull up an image of a galaxy. And because Angie asked the question, I'm going to pull up a galaxy that I'm sure she would like. It's the M83 galaxy. Yes, just like the band or the musician or whatever you would call him, M83, which is actually named after this galaxy, by the way. This is, I'm going to put it up for you guys. This is Messier 83. One thing that you'll notice right out of the gate are the colors, right? And we can learn a lot from the colors. So first of all, you'll see there's a lot of blue going on in here. Now, stars burn in different parts of the spectrum, and they are mostly white. Like, this is like white-blue, right? But if they shine towards the bluer end of the spectrum, that means they're hotter. It means they're larger stars. They're big, hot stars. Smaller, redder stars tend to burn more red, of course. And then there's like that weird exception where a star at the end of its life will swell up and get bright, but cool down because it's swelling, and so they are red, and those are the red giant stars. So all this blue you're seeing are the bigger stars in this galaxy that are outshining the others for the most part. And so you're getting all these bright blue guys. But the thing about those big, bright blue guys is a star's life is correlated to its size. And it's sort of like the difference between an SUV and a Prius. The fuel tank may be bigger in an SUV. The Prius is going to take longer to go through its fuel, right? Even though it has less, because it's at better gas mileage, right? It's more fuel efficient. Stars are that way. Smaller stars have better gas mileage than big stars. So even though big stars have more fuel for the fusion reaction that goes on inside them, they burn through it quicker. And so big stars live shorter lives. And so what this tells me, when we look at this galaxy, we see all this blue, these are all young stars, right? They're not as old, because if we give enough time, those blue guys will all die out, right? So the color of a galaxy, these bluer spiral galaxies are still forming new stars, because that's, otherwise if they weren't still forming new stars, if they were older and enough time had passed, all those hot, bright, big stars would have died. They would have all exploded, and the galaxy fades to a different color, right? They get more amber in color, and I'll show you an example of that in a second. So this tells me something about the age of this galaxy, and in fact, the fact that we tend to see spirals as blue suggests that spiral galaxies may be an earlier stage in galaxy evolution, that these are young galaxies that are still actively forming stars. But the second thing you'll notice is all this pink. There's just pink all throughout here, pink and purple. And this pink color is associated with what we call an H2 region. That's ionized hydrogen. No, sorry, molecular hydrogen, right? Hydrogen and hydrogen, H2. This is molecular hydrogen nebulae, gas clouds, but normally they don't light up. So you see all this like gray, smudgy, brown stuff here, right? Those are also clouds of mostly hydrogen and stuff. But the pink ones are glowing, and they're glowing because new stars are forming within them to illuminate and to make that gas glow in that hydrogen part of the spectrum that is so difficult for the eye to see. And so when we look at pictures of other H2 regions, I can pull up an H2 region. H2 region. What's a good example? Ooh, the Lagoon Nebula. All right, here's a good example of an H2 region. You see how reddish pink they are, right? It especially looks pink in this longer exposure photograph right here. So this pink in the galaxy also tells me that there's a lot of star formation going on. In fact, one thing that we sometimes will see, I'm going to bring up a really good example, the antenna galaxies. I love how Google starts to figure out that I'm doing all space stuff. All I have to type is antenna and it already knows what I mean. You see, well, that doesn't look like a great picture. You see all the pink in this galaxy. And the reason for this is actually two galaxies. You can see the core of one and the core of the other, and they smashed into each other. And the force of that smashing together compressed all these gas clouds and caused a whole bunch of stars to form. And so sometimes when these galaxies hit each other, they light up pink. It's actually really cool. And that's an indication. That's an indicator of star formation. That's one way we can tell there's new star formation. Here's the bigger picture, so you can really see that they're colliding, right? You really get the impression that they're smashing into each other. And why we call them the antenna galaxies, because it looks like an ant with its antennae. So now I'm going to bring up Messier 87. Right? And of course, we get a lot of pictures of the black hole. The black hole is very famous. We could talk about that too. But here in this picture, you see how this galaxy is loading slowly. Because I had to click it too many times and make it blow up real big. Here we go. But you see how this is a more muted color. It's a bit more amberish, right? Mostly white, yellow, maybe a bit of red mixed in here. Stars, right? This is a very old galaxy. This is one in which all the biggest, brightest, bluest stars have all since died. And so we're left with these smaller, longer-lived stars in the redder part of the spectrum, right? So again, the color of the star teaches us a lot about the age of the galaxy. Did I say star? Of the galaxy. The color of the galaxy can teach us a lot about the age of the galaxy as well. And somebody said, being that they're a French band, it makes sense that they chose a Messier object. Right, because Charles Messier is French, right? And in fact, I think I read that about them, that they were like that the Messier list is something that is, you know, a bit of French pride for them, so they went with something from the Messier list. Prasana says, I always hear you guys talk about power, where you increase or decrease based on object you are seeing and changing different eyepieces. If you can talk about the importance of power and what role it plays. Yeah, so it sounds like the questions tonight are largely geared towards observing rather than the objects itself, which is fine. That's also a valid topic of conversation. So as long as you guys are still interested in learning about telescopes and observing, we can talk about that too. So power. When we talk about power, what we mean is magnification, right? Just like with a microscope, you have like times this power, times that power. We're talking about magnification. And with a telescope, we change magnification by changing the eyepiece. The formula is real simple. You take the focal length of the telescope, you divide by the focal length of the eyepiece. There's your power. So just as a really simplified example, let's say we have a telescope 1,000 millimeter, and these are always measured in millimeters, 1,000 millimeter focal length, and we have a 10 millimeter eyepiece. 1,000 divided by 10 is 100. So that's 100 times magnification. So right out of the gate, we can already guess that the one benefit of power is you blow up the image. You see it bigger, right? Now, there is a trade-off, though, because physics always applies, and we can't get away from it. And there is a correlation between the brightness and the magnification, which is as we magnify an object and we blow it up more and more, we're taking the same amount of light and we're spreading it. We're smearing it across more and more of the view as we're zooming in on it. And we're forcing it through more glass and this kind of thing. And so your object is going to get dimmer and dimmer as you magnify. So this is one reason why we don't just go out there and throw our highest power eyepiece in, because you might think, okay, well, you're looking at this thing, it's 25 million light years away, right? Andromeda galaxy is 2.5 million actually, or 25 million some of these galaxies or whatever, and it's this big and it's a little smudge on your view. So why not just crank in on it? Why not just throw the highest power eyepiece you have? Well, the problem is that it gets dimmer as you go. Right, the object is going to get dimmer and dimmer as you zoom in and in and in, and so there's a trade-off where it becomes harder to see the object, right? Because the object itself is faint. Now, that being said, you might think then that the policy is, if I want to see a faint object like a deep sky object, I should throw in my lowest power eyepiece. And I actually used to advise people that, but I've since learned that there's actually a bit of a back and forth. Well, first of all, you don't want to throw in an eyepiece so low that the object is this big and you don't see anything, obviously. But also, when you go down in magnification like that, not only are you not decreasing the brightness of the object, but the background as well. And so there's a point where with a little bit of magnification, a little bit of extra power, yes, the object's going to get a little dimmer, but sometimes the background dims more quickly, if that makes sense. And so you dim the background light pollution more than the object, and you can actually help increase the contrast a little by cutting down the light a little bit, right? So sometimes a little bit of higher power helps for that reason. The other thing is that we have to talk a little bit, and this is getting, I'm about to get into the weeds. And I always tell people that this talk is meant for all levels of familiarity and skill. So if you're an absolute beginner, somebody who knows nothing about astronomy, and you were just coming to learn about planets, I apologize. Bear with me a second. We're going to get a little in the thick of it. I promise we're going to come back out on the other end. But I do want to answer this question because this is a really interesting topic. And I'm going to bring up the human retina again, right? Do I still have that picture somewhere? No. Okay, retina diagram. So one thing that happens is we increase in magnification. Where is, man, now I can't find it. Okay, you know what? This is actually a good picture. So this thing right here called the fovea, it's a densely packed group of cone cells, which for the most part don't do us any good when we do deep sky, faint object things, but around it there's a bunch of rods. So the fovea is still important. So when we are using an eyepiece, the lower the power, the bigger the beam, the sort of cone of light that comes out of the eyepiece and hits you in the eye, right? So as we go down in magnification, you eventually get where so wide of a image of light is coming out of that eyepiece that you're spilling some light on your iris. It's not all getting into your pupil, and it's not all doing you any good. So as you go down in magnification and your clarity and brightness, because also I forgot to mention it gets blurrier too, and I'm going to explain why. There is a minimum effective magnification below which you're not getting any benefit from going down in magnification. The other direction, though, as we get to a high enough power and that beam of light shrinks and shrinks and shrinks, it's hitting a smaller and smaller and smaller piece of our retina until it's only hitting such a small number of rod and cone cells that it's kind of like a low resolution image on your TV, right? Even if the object is bright enough to be able to see it, you're using so little of your retina at this point that you're losing the benefit, that the resolution is just too low and you're not getting any benefit there. So that means that there's an effective maximum amount of magnification. If you're shopping for eyepieces, and again, I'm going to try and keep this really surface level and come back around to some beginner friendly stuff. But if you're shopping for eyepieces, you're thinking about getting a new telescope, this is good to know. You can learn about something called exit pupil. The calculation for exit pupil is you take your eyepiece focal length and divide it by the F ratio of your telescope. If you don't know your telescope's F ratio, you can literally just Google your telescope and look it up. Mine's an F5, and that'll tell you. And so you could also run the formula in reverse. If you want to find a particular exit pupil multiply that by your F ratio, and that'll tell you what eyepiece to buy. And the magic numbers, and again, I'm just going to kind of leave it on this and move on to the next topic so it's not getting too into the weeds, but the magic numbers here are 5, 2, and 1. Actually, they're more like 7, 2, and 0.5 if you want your actual maximum and minimum. But I would say if you're buying a new set of eyepieces and you're starting your collection, err a little bit on the side of caution because you rarely get your theoretical minimum and maximum. So 5 millimeter exit pupil, 2 millimeter exit pupil, and 1 millimeter exit pupil. Which means that if your telescope is an f5 like mine is, 5 times 5 is 25. So a 25... Hold on, did I do this right? And now I'm second guessing because I got different... Yeah, no, that's right. 5 times 5 is 25. So 25 is a good low end for an f5 telescope, right? For a low power eyepiece, 25 millimeter eyepiece, boom, buy that one. 5 times 2 is 10. And 2, the reason why 2 is special, it's like a sweet spot. It makes the best use of your fovea. It's that exit pupil that is the same size as the really sensitive part of your eye. So it's like the perfect blend of magnification and brightness. It's like right there in that sweet spot. So for my telescope, that's about a 10 millimeter, and then 5 times 1 is 5. So a 5 millimeter eyepiece is the smallest exit pupil that's going to do me any good. If I go up above 5, I'm going to start to get really blurry, and it's not going to look great. So that's a good rule of thumb if you're buying eyepieces. Find the F number on your telescope, multiply it by 5, buy that, 2, buy that, 1, buy that. And if you're going to splurge on an eyepiece, splurge on the one that's going to give you the 2 millimeter exit pupil. So again, with my telescope as the example, I would want to splurge on a 10. And that's actually why, or something near there, right? So I recently had the opportunity to buy a $300 11 millimeter eyepiece for only $200, and I pounced on it because that's 11 millimeters is right there for my telescope, and there's a reason this is a $200 eyepiece. They are awesome. But so that's if you're buying eyepieces. And that's all I'm going to really say on exit pupil and eyepieces and magnification, because again, I don't want to get too into the weeds on this. But obviously, Process, you're in the club. You can pick my brain anytime about it. And of course, if anyone watching this does want to get deeper, email me, right? You got my email, membership@nefis.org. But that's a bit of information about eyepiece and magnification and power and how to use it, and why we do sometimes want to go up a little bit in magnification on these faint objects, even though that seems counterintuitive, right? Because you think, well, it's going to get dimmer and it's going to get blurrier, but a little bit of magnification is going to increase contrast. The other thing, though, is for bright objects like planets and the moon, man, go nuts. Go nuts. That's when you're going to use your guy that's going to give you the 1 millimeter focal length. That's when I use my 5 is on planets and stuff, because they're so bright, you don't have to worry about, I'm going to make Jupiter too dim to see. No, man, you can just crank on it. You can just get right in there. Make it a little blurrier, right? So, again, don't exceed your theoretical maximum, but that's a good... thing to keep in mind as well is it depends on what you're looking at. Solar system objects, the particularly bright stuff, you can really go in on them. And then for fainter objects like galaxies and nebulae, you're probably going to be looking at your somewhere between the sweet spot and the low end eyepiece. One other thing about magnification, this is also good for all beginners to know. Whenever you go out, when you're going to find an object, so I'm going to bring up Stellarium and pretend that I'm going to find something, pretend I'm using my telescope. And I am going to try and find the Leo triplet. Let's say I'm going to try and find the Leo triplet. So I look at my star chart, and my star chart shows me that it's about halfway between these two stars, maybe a little bit to this side of this center line, okay? So I am going to point my telescope right here, right? What I'm going to want to do, what I don't want to do is just slam my highest power eyepiece like this and go, I don't know. Right? What you want to do is start off low power like this. And then you find, oh, here it is. Center it up. And then if I want to try zooming in a little bit, then I'm going to switch to a higher power eyepiece. See how I like that. Right? If it can handle a little bit more magnification, maybe do a little bit more. But you want to start off low and step up. Right? Because one other thing that you might have noticed right now as I'm simulating this effect of higher power eyepieces is that not only is the object getting bigger, right? But look, this is the piece of sky I look at with one magnification. If I zoom in, I'm only looking at this much sky. So lower magnification is showing you a bigger piece of the sky than higher magnification, right? It's looking through a window versus looking through a straw. And so you want to start off low power while you're looking for the object, center it up, and then you can start to scale up. And when you're first starting off and you're still learning and getting a feel for it, just experiment, man. You got your eyepieces all there. You know, there's no race. You're not in a competition to like see more objects than the guy sitting next to you. If it was a competition, I'd lose every time because I sit and I spend 45 minutes sketching one thing. Right? So believe me, take it from me, there's no problem taking your time on an object. And by all means, get in there and swap out. Try this eyepiece, try that one, maybe swap back. Let me try them both, see which one I like. I think I like that one, whatever. With experience, you'll develop a feel for it. So now when I have my 25 in and I line up a galaxy, I look at it in the 25 and I go, this would probably handle my 8.8, right? Or I might go, yeah, I don't want to zoom in on this. This is probably good where it is. Or maybe I can throw my 25 into a Barlow so it's more like a 13, right? Bearing in mind, of course, that the smaller the number on your eyepiece, the higher the magnification, like I was saying before. So experience, you'll get a feel for what, when you look at an object, you get an idea, you kind of know what you can do. But to build that experience, just play with it. Just experiment with your eyepieces. One other really good beginner thing about eyepieces while we're on the subject, once you've bought your three that I mentioned there, I like to call those the three amigos, 5mm, 2mm, and 1. Not that those are the size of the eyepiece, but multiply that by your F ratio of your telescope and buy those. Another thing you can do is buy something called a Barlow. They come in ×2 and ×3. Look at the relationship between your eyepieces and buy the Barlow that isn't that, right? So if your lowest power eyepiece, your middle, and your high are like half, half, and half, you know, like a 20, a 10, and a 5, then buy a tripling Barlow. Don't buy a ×2 because it's redundant, right? But what a Barlow does is it basically doubles your eyepiece collection. Or if you find that they're not like that, like in my example, I got 25, 10, and 5. I use a ×2 Barlow, right? Because it fills in some of the gaps. And so what it does is it basically doubles the power of whatever eyepiece you put in it, and then you put it in the telescope. And so it's a cheap way to basically double your eyepiece collection, right? And again, you may decide when you're looking at these three amigos that you go, oh, well, I want to buy a 10 and a 5. Maybe I'll just get a 25, a 10, and a Barlow, right? And that covers my 5. So, another little thing to keep in mind when you're buying eyepieces. And so, yeah, and so then you could experiment with those combinations, try it out on different objects, see what looks better, and you'll eventually get a feel for it. All right. I think I've just about answered everybody's questions, and I'm loving it, by the way. I'm loving the engagement. This is what I'm always trying to get, man. Ask these questions, bring them on. Like I said, a lot of questions tonight about observing, which is cool, which is exciting for me because it means that people are interested in observing, right? Mind you, I actually personally know everyone who's been commenting, but nonetheless, I'm sure there may be some people watching who aren't commenting, and hopefully you're finding this, informative. And if you came here to learn about planets and we've done nothing but talk about equipment, chime in, man. Let me know you want to talk about planets or whatever. We can talk about that too. But so far, the people who have actually been, participating in the chat, they've been asking a lot of questions about observing and actual learning about how to observe. So I've been focusing on that. But while I wait for more questions, I am going to get back to some more general astronomy stuff just to kind of even things out a little bit and give people a chance to process that pile of info I gave them. I was talking earlier about finding other constellations. I completely blanked on this. I showed you how to find several things from Ursa Major, but here's the really obvious one. Take the edge of the ball, shoot right down here, North Star. And then usually the edge of the bowl, you see these are kind of brighter stars. And this one, unfortunately, you see these guys in between are kind of faint, right? So the Little Dipper, which is what this is a little harder to find on its own. But you can use the Big Dipper to find Polaris, find the edge of the bowl, and you can start looking for the rest of the Dipper. I mentioned before that right now we are fully in the swing of galaxy season, and I was starting to talk about why that is. So, galaxies, it turns out, are not just strewn about the heavens or the universe. The truth is that galaxies actually clump together. And by the way, my mustache itches my nose, which is why I do this all the time. But I still like it. But anyway, so galaxies are organized in like clusters, right? They kind of clump together. And so there's areas of the universe where there's a lot of galaxies. And in fact, these clusters themselves clump together and they actually form, it's really interesting, they form these big long filaments, these big stretches of just an unbelievable number of galaxies. And then from one filament to the next is an unfathomable nothingness. It's actually like freaky to me, this notion that if you somehow left one of the filaments, that there's millions, like hundreds of millions of light years of nothing, of just nothing, until you hit another filament loaded down with galaxies. But our filament, Laniakea, includes something called the Virgo supercluster. Our galaxy happens to live more near the outskirts of the supercluster. The heart of the supercluster is filled with a whole bunch of those big elliptical guys, some spirally guys, and that kind of stuff. And so if I pull up here on my visual aids, now this is an artist's recreation. We can't leave the galaxy to look at this from the outside. This is an artist's recreation. But if I'm going to pull up the Virgo supercluster, and I'll say in a second why we call it the Virgo supercluster, why it actually has that name. This I think is a good. This one I think is a good image. And yeah, this one's got like "please don't steal me" marks all over it, so that's fine. I'm not trying to steal it. I'm just going to use it as a visual aid. If you guys like this picture, by all means, pay for it. But this is the Virgo supercluster, and you see this little thing here says local galactic group. One thing I don't like about this picture is this doesn't tell me which of these dots is which. Every single dot in this image is at least one galaxy, maybe even a few of them clumped together, right? Entire galaxies, mind you, not individual stars. A galaxy, which itself is oftentimes as many as 100 or so billion stars, maybe even more, hundreds of billions of stars. Our local galactic group is this little clump right here, right? And if you look over here, man, this is where it's at, right? This right here is the Virgo cluster, which itself is the heart of the Virgo supercluster, which you can see is forming a bit of this filamentary structure. And then if we zoom out more, to Laniakea supercluster, right, then we can really see, oh, this is the Laniakea supercluster, okay, right? And so eventually you get to a high enough scale and you get this weird filamentary pattern. It's really cool. But anyway, my point, bringing it back down a little bit to Laniakea, is that when we're over here in our local group, we can look this direction towards the heart of this cluster. And it just so happens to be that the direction you would look to see that is the direction somewhere here, partway between Virgo and Leo. And that's why we call it the Virgo supercluster, because most of the stars, because there are some down here and over here as well, up in Coma, Berenices, it's all over the place here. But this chunk of sky is where it mostly is found, with the highest density being in here. And the thing about constellations is we don't think of the constellation just as the individual stars. We actually astronomers draw borders around them. And so whenever we say that an object is in Virgo, an object in Virgo could be here, right? But it might be that the border of Virgo technically includes it. So even though it's easy to think of this supercluster as being halfway between Virgo and Leo, this piece of sky, the border of Virgo kind of comes through here. So this piece of sky belongs to Virgo, which makes sense, right? You got to include the arms in the border. And so it happens to be that during this time of the year, we can look straight into the heart of the supercluster to which we belong, and we're looking in from the outskirts. And so it's just absolutely outrageous with galaxies. There's more going on here than just the Virgo supercluster. We also have the Leo cluster, the Virgo cluster, which is in here, which is part of the Virgo supercluster. So basically, the supercluster is all of these things. The Virgo cluster is the thickest part of the supercluster, so the supercluster takes on that name. But there's also the Coma cluster, which is up here in Coma Berenices. If I start to zoom in, start to see there's a whole bunch of galaxies up in here too. There's one. This is actually something else. That's not a galaxy. There's a galaxy. Here's a bunch of galaxies. All right, this guy right here. There goes one, right? So there's also the Canis Major, or the Ursa Major cluster, right? So if we go over to the Big Dipper, there are actually a bunch of galaxies by the Big Dipper as well, meaning that as far as the Big Dipper is concerned, it's galaxy season all year round. But because we have Ursa Major pretty much all year round. We got M108 over here, next to the Owl Nebula, which is actually part of our galaxy. We've got over here, we got M81 and M82. These are cool. They're kind of bright. They're sort of like that border between really bright, easy objects that are cool to show people when you do outreach in the middle of a neighborhood in Orange Park versus the really deep, faint stuff that you have to get out in the middle of nowhere to see. These guys are kind of halfway. And so when I do my outreach, I like to show these to people sometimes and be like, okay, this one's kind of challenging. You know, I like to give people a little bit of a taste of more than just the Andromeda Galaxy. That's just me. And M81, 82 are good examples of that. A really cool one that's over here is if we find the tip of Ursa Major, and we find this star, the exact equal distance this way, right? So we're looking about here. If we zoom in, here it is. There's this guy, M51. This is one galaxy eating another. And this guy looks really cool. Prasna can tell you, I've mentioned this multiple times. So he said galaxies and globular clusters. Yay, yeah, awesome, right? Both really great stuff. Prasna can tell you that I always like to say that M51 is odd. It likes to hide sometimes, and sometimes it likes to jump right out and say hello. It's just one of those weird galaxies. It's very finicky with the sky conditions. If you've got even a little bit of light pollution, M51 will just say nope, and it will hide in the background. But if it gets dark enough, it'll jump right out at you and really show you all of the beauty of this galaxy. So it's 51. Some days it's hard, some days it's easy. It's weirdly hit or miss, but it's a cool one to try for, and always a good one to see if you can see it. So yeah, this time of year, if you like galaxies, if you're interested in galaxies, now I will tell you, if you're getting into visual, and again, a lot of the comments tonight have been about visual, and all the people commenting I know have or are thinking about buying telescopes, then I know you guys are getting into that, so that's been kind of the theme tonight, which is cool. If you're getting into visual astronomy and you want to go deep sky, you want to look at things outside the solar system, galaxies, nebulae, star clusters, galaxies are probably the hardest. No, actually, nebulae. The nebulae are really, really hard, but galaxies are up there too. Star clusters are probably the easiest deep sky objects, followed by galaxies and then nebulae. But galaxies are challenging, but they can be very rewarding if you're patient. But expect to see a lot of just little blur, little smudge. The advantage that most galaxies have, especially the spirally guys, the ellipticals are not quite this way, but the spirally guys tend to be well defined. They have a clear edge to them, and then a nice contrast from the background. Nebulae are oftentimes difficult to find because they just fade. And oftentimes they don't have like a hard edge, and they just fade right into the background. Some nebulae do. It depends on what you're looking at, but so nebulae can be a bit of a challenge as well, and galaxies. But yeah, right now, galaxy season is in full swing. Not tonight, though. The moon is right here ruining everybody's fun. But unless you want to look at the moon, of course. But it's going to blow out pretty much every galaxy in this piece of sky. To give you an idea of what I'm talking about when I say galaxy season, not last weekend, but the weekend before, again, Prasna was there, Chris was there, some of the people from the club were there. We went out to our observing site called the Swamp. 2 nights in a row, Friday and Saturday. Between those 2 nights, just in the constellation Leo, I sketched 21, 22 galaxies. Just one after the other, after the other, after the other. Just in this one constellation, just knocking them down. So, if you like galaxies, man, now is the time of the year. Yeah, and as Richard mentioned, planetary nebulae are hard for certain. I say this every single time I do a presentation and planetary nebulae come up, and they always do. That is the dumbest name for anything ever. If you don't know what a planetary nebula is, it's the remnants of a dead star. Has nothing at all to do with planets, but that's just what they're called. Um, and yeah, some of them can be. A lot of the planetary nebulae are difficult because they're just so small, right? It's just a star really far away that died and went poof and left us a little circular spherical cloud of gas. So sometimes it's hard to tell them apart from regular stars. When you look at your telescope, you see all these little pinpoints. Oh, that one's slightly circular, right? That one popped. The other ones didn't. That's really, they can be that hard. And then some of them are like the helix, and they're big and beautiful, and they fill up your whole view. Um, Florida Dance Gypsy says, I have a 12-inch knob, and I am not able to see much definition in galaxies except maybe a bright center. Do my eyes need to be trained to see spiral arms? That's a really good question. Which, like a lot of the questions, the answer is yes and no. For one thing, 12 inches, that's a good size. Mine's a 10. I use a 10. 12 is good. For most of them, you won't see the arms. Honestly, most spirals you really won't. I think I can find a way to show you guys some of my sketches. And if I show you some of those, let me see here. Just gonna try and add an image real fast. Actually, let me. Yeah, let's see here. Okay, and if we move this over, right here, you see these two blurry smudges? Those were spiral galaxies, right? Those were a couple of spiral galaxies I saw through the eyepiece. Let me see if I can give you another example here. Where did it go? Here we go. Let me try. You know, I'm going to pull up the Leo triplet so you can see what my sketch of it looks like, right? Leo triplet. Okay, I thought I pulled it up. Let me try that again. Okay, I think this one is a much lower resolution than that last picture, so it shrank. Here you can also see I do. This is what I do, by the way. This is how my log entries look. I Z10 is my telescope. It's a Zubel Z10. It's a 10-inch telescope. I'm going to move this picture down so it's not blocking my face. There we go. And I determine which way is west, and I draw a little picture, right? And this is what I do. This is how I take my own observations. See these little faint little smudgies? That's all I saw of the Leo triplet when I looked at it visually. So for the most part, most of the time with spiral galaxies, you're not going to see the spiral arms. Actually, even a really close one like Messier 33, which is particularly close and particularly bright. If I go back to my logs and I look for M33. Yeah, this one back up to higher res. This is what I saw with this one. And I will show you what it actually looks like. Bring up visual aids, and then we go to Messier 33, right? This is what it actually looks like. The trick with the galaxies, spiral galaxies are actually oftentimes even more difficult because they're flat, right? So you picture the galaxy as flat, and the galaxy is not a solid object. It's a tenuous object. It's made up of a bunch of stars. It's mostly nothing, right? Most of the galaxy is the empty space between the stars. And so you're thinking of it, you want to think of a galaxy like a cloud of smoke. If you look edge on, you look through the smoke, you actually see it brighter and more easily than if it's turned like this. When it's like this, you easily just see right through it, and it blends into the background. This is why M51, I mentioned earlier, likes to play hide and seek, right? M33 likes to play hide and seek. Sometimes this thing is impossible. Other nights, I've literally seen it naked eye, right? So this is, it likes to play hide and seek as well, and you usually don't see the spiral arms. Now, the reason why I said that the answer to the question of can you train yourself to see the spiral arms is yes and no is because there definitely are techniques you can learn to be a better observer. One thing, and this is not a technique, but your 12 inches of aperture, that's helping you out because that's going to gather a lot of light for you, right? When you see a galaxy, again, I know instinctively you might be afraid to put a little magnification on it because you're worried you're going to like lose that tenuous amount of light. But do experiment a little bit with it, throwing a little bit of magnification on. Sometimes dimming it down a little bit will help to bring out the contrast and will make some of its features become more apparent. Some of the details will become a little bit more apparent with a little bit of increased contrast from a little bit extra magnification. So sometimes with a galaxies especially, a little bit of power helps, right? I found these days for my telescope, I tend to use a 14 millimeter, which is my 26, or 13, I should say. It's my 26 in a ×2 Barlow. That seems to be like a great combo for a lot of galaxies for me. That helps to increase the contrast. Another technique you can use is called averted vision. So when you're looking at the object, you don't look dead at it. You look next to it, and you move your eye around it, right? So you move your eye around here, 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 and here. And that's because earlier when I was talking about the structure of the eye and the fovea, how you have that sensitive area called the fovea, the center of the fovea is all cone cells, which are bad at detecting faint light. And when you look directly at something, you point your fovea at it. So if you look next to something, you're moving the cones over, and you're letting the rods, that dense area of rods around the fovea, get in on the action. And so that will help. And sometimes you'll see out of the corner of your eye. Tapping on the telescope to introduce a bit of movement helps because the way your brain processes visual information from the eyes. Creating difference helps. So when the object moves, your brain notices the motion and sees more than if it sits still and your brain starts to ignore it. So introducing a bit of motion helps. And the last thing is experience. Experience. Just looking at these objects, looking with averted vision, maybe tap the telescope to introduce a bit of motion, take some time. I recommend sitting comfortably, get an observing chair, sit comfortably, relax the muscles of your face. Sometimes you squinch up when you look through. I even do this so you're nice and relaxed. One thing I'll do if anyone's ever like close to me while I'm looking through a telescope, you can probably hear me going, because I don't know about anybody else, but for some reason when I do this, I forget to breathe. I literally forget what breathing is, and then I've like looked at something and gone, and then I realized I hadn't been breathing, right? Give your brain oxygen. That helps. And be comfortable and take your time. The other thing is your eye will build up an image over time. So it's not quite a CCD chip, but your eye can build up an image over time. So if you sit and you spend time with an object, you look near it, right? These are all ways you can increase what you see and take your time with an object. And with experience, you will learn to see more by using these techniques, but also just by learning what to look for. A great way to train your observational powers is through keeping a log. And I'm always banging this drum because I'm like the only guy who I know who does it. But genuinely sketching sketching these objects helps train you to be a better observer, because when you do, if you're sitting there and you're taking your time and you're sketching something, you're going to look for details to sketch or to write about if you're just doing a written description. And you're going to start to say, like, for example, when I observed M33 when I made that last sketch, I couldn't see any arms, but I was taking my time and I was looking at it using averted vision. And I thought, you know, I can't see the arms. I couldn't say there's an arm here. But it does give me like an impression like it's got a twistiness to it, right? And if I had to say, is it turning this way or this way, I would say it's turning this way. And I look it up later, and in fact it is, right? Even though I couldn't make out the arms, in my notes, I'm like, it seems to have a chirality. It seems to be rotating a particular way, right? And doing this, again, you train yourself to see more over time. So that or sketching also can help you to see more. And you can train yourself to be better at it, but it is the case that most of the time you're not going to see spiral arms when you're looking visually, unless you're looking at a particularly large, particularly bright, and particularly well-defined spiral. If you want to see... I turned off Stellarium there for a second. If you really want to see spiral arms, though, and you want some suggestions, there are a couple of galaxies that are really good for it. One of them is actually M51. Most of the time when you look at M51, what you're going to see, and I'll show you a sketch I got of it the other night here in a second so you can get a real good idea, but most of the time what you're going to see is a blurry patch with a bright center, a smaller blurry patch with a bright center. Sometimes you might get a sense they're connected, right? And that's a bit of a hint of a spiral. That's actually something cool. Sometimes it'll just feel like it's got a bit of a rotational thing, and then sometimes when everything lines up perfectly and you're having the best observing night of your life, you can start to tease out these arms. So with my 10-inch, I got this sketch recently. Let me pull it up here. This one, right? So here, right, if we compare this, if I'm going to pull up the actual M51 here for you guys, Messier 51, you're going to see that my arms don't quite correlate to reality, because I was drawing from the faintest impression of an arm. I'm like, God, it really seems like I can tell there's a brighter area here, brighter area here. If I turn on visual aids, oh, and I have to move this image down. Right, this is the actual object, my sketch, right? So with a lot of patience and some experience and building up, because observing is a skill that you can train like any other skill, sometimes you'll get spiral arms. And so 51 is a good one to go after if you want to test your ability to actually see the spiral arms. Another good one, and I can never remember its name. I'm just gonna, or its official designation, because it's NGC something, but they call it the Great Spiraled, the Great Barred Spiral Galaxy. NGC 1365. NGC 1365. All right, so this guy, bring on the visual aids again. This one right here, this is a really good one if you want to pick out spiral arms. It's not an easy one to get. It's kind of far south. I got it from the Florida Keys. I've seen it from our swamp site, but it's getting low. It's not easy to do. But it's, if you can find this one, NGC 1365, I'll put it in the group chat for everybody. A couple people complimenting me on my sketching. Love it. I appreciate it. Looks like, oh yeah, I got a lot of comments on the, oh wow, got a lot of activity in the chat. I'll come back to that here in a second. All right, NGC 1365, Great barred spiral galaxy. That's the name of it. That's another really good one to go after if you're looking to see arms, because you see how very opened up it is. It's pretty much anywhere you see the galaxy is an arm, right? It's not all coiled up. It's just open like this with this nice big bar in there. I actually have a sketch of that one too, since you guys seem to like my sketches. So let me pull up the sketch I did of it. And somebody asked me if I'm using chalk on black paper. Actually, I'm using graphite on white paper, and then I invert the colors in the computer. I scan it, and I invert the colors. I'll have to show you an example of what they look like before I do that. Okay. NGC 1365. This was my sketch of that object. Now, mind you, if you look at my notes, I'm using a 16. I'm actually borrowing, and this is the focal length, 1825, so I could calculate the magnification later. I was actually borrowing Mike Napper's 16-inch telescope while we were down there in the Keys. But you see, I got the thing, the bar in the middle. One really cool thing about this galaxy, it actually has two bar features. There's this central bar, and then there's another bar kind of at an angle to it, a smaller bar. And then you got one arm coming up and one arm coming down, and there's a star right here. Don't know if that was a star or if maybe I got really lucky and caught a supernova. Not sure. But yeah, so there are a few options out there if you really want to actually see some spiral arms. But for the most part, you're right, you're not going to really see them. So I'm going to hop in the chat real fast because I didn't realize that there has been a lot of discussion here. Somebody mentioned using an eye patch on your non-observing eye so you don't have to force close it. That's a really good call. Some people will actually do the opposite. They'll keep an eye patch on the observing eye. So this one, they're still using red light and they're reading and everything, but this one's kept protected and then they open it when they look. That's a thing that some people do as well. I've never really gotten that one to work, but I might try just patching the non-observing eye. Somebody mentioned Chris's 18-inch scope. Yeah, there's the other thing, man. You look at the M51 through an 18, you will see the arms. You will see those spiral arms. Let's see here. Sometimes see more detail the longer you study. Yeah, exactly. Richard agrees. You spend time with it, you build up an image, you see more. And so we'll talk a little bit about the sketching. So got a couple of people asking about the sketching. What I do is I have white paper. I use heavyweight paper so that it's more like what you'd find in a sketch pad, and also for durability, so it holds up to the dew and things when we're out there. And I pre-print those sketching circles and things on there. And when I find an object that I'm going to sketch, I sit there and I take my pencils and I add the stars. And there's just dots. I do the same convention like Stellarium. Bigger stars, I make them bigger. And then what I'll do is I'll scribble some graphite near the circle. And I take what's called a blending stump or a tortillon. You could buy them super cheap, like a pack of like 10 of them for $3 at Walmart or Joann or wherever. And I rub that in the graphite, and then I rub it in to smudge in the blurriness of the blurry objects. And then with erasers, I can also remove a bit of graphite. And what I do when I'm sketching is I make a negative, right? So I sketch it such that the white background is the black of space. And then the graphite that I'm laying down is the lighter objects, the light of the stars and the nebulae and whatever. And so what I do is I make it such that the brighter areas of the object, I smudge those in darker. And I actually have a couple different pencils. I've got an HB, which is the equivalent of a number 2. And artist pencils, by the way, they measure it on a scale of hard to black, which is a weird way of measuring it, but basically harder pencils are more silvery, and then softer pencils are dark and black. So I use an HB, that's like your number 2, and then I have 4B and 6B, which are dark but soft graphite that I can use. So, for example, if I bring it back up again, you see how the core is brighter than the rest of the galaxy, and you see how, if I move this over slightly, I've got 2 different colored patches of graphite here. That's because I had the 2 different pencils. And that's my technique. And I put those in, and I get it to looking good. I've got a red light on my forehead shining down, doing my best. And then I scan that on a scanner, and then I invert the colors later in the computer. And that's how I get that. So to show you real fast, I'll actually find this same one. How about that? And I'll show you what it looked like before the post-processing. So this is what it looked like when I first scanned it into the computer. This is what the page looked like, right? And all of this. And then I invert that and I get the negative, which is the object that I'm getting. So that's my technique. There are people that do actually use chalk on black paper and different techniques. I like to use the graphite and the pencils. It works well for me. For some objects, I don't invert it, obviously. Like when I sketch the moon, I just sketch it as is. And I've only sketched the moon a couple of times. I'll take a quick second to shamelessly brag on myself here if I can. Because I do have, if I can say so, some decent sketches of the moon. So this is my sketch of Mare Imbrium. Oof, that is big. Can I shrink this down a little bit? All right. There we go. And then one more here for you guys. The Theophilus crater complex. This one I'm really proud of how it turned out. This was my sketch of the Theophilus crater complex. So obviously for this one, I don't invert it because this is how I want it to look. But that's a little bit about the sketching. We've got about 8 minutes left. And the thing, someone said, tell them how to determine north. Okay, yeah, that's actually a good thing to talk about for the remaining 8 minutes. Or not Chris, sorry, Richard. We got two different guys in our astronomy club whose username is something surf. Because we got a couple of surfers in the club. So I keep calling you Chris because I know he's a surfer as well. This is Richard. So one thing to note is that the sky is going to drift to the west, right? That's because the Earth is rotating the other way. The Earth rotates towards the east, right? And so it gives the whole sky this westerly rotation. If I zoom out and I go hour by hour time traveling, all right, things head to the west. Which means that if you're looking at an object through a telescope and you don't have a motor tracking it, you're just looking like this, you see how it's moving on us? It's drifting. That tells me that that direction is west, right? This way is west. Once you find west, you could find the other directions because I know the other way is east, right? So that's two directions. And then depending on how many mirrors your telescope has determines if you're going to want to go clockwise or counterclockwise. So with a Newtonian telescope that has a mirror at the bottom and a mirror at the top, so it's an even number of mirrors. Once you find west, go 90 degrees counterclockwise, and that's north. If you have a telescope that uses an odd number of mirrors, like a refracting telescope with a diagonal at the bottom, or a Cassegrain that has the mirror at the back, mirror at the front, and the diagonal at the bottom for a total of 3, you go the other direction. You go 90 degrees counterclockwise, and that's north, and the opposite is south. That's how I determine north. So all my sketches, I have a little thing on the bottom there where I indicate which direction is north, west, east, and south, and that's how I do it. So if you are keeping a sketch log, you want to do that. Or even if you're just keeping a handwritten log, it can be really useful to figure out that this is west, this is east, and this is north. So if I'm describing this object, I might say, large, somewhat circular, fuzzy galaxy, very bright core, second core visible to the east, somewhat smaller, appears to be connected by a small piece of material or something, right? So to be able to say that it's east is useful, or to be able to say not east, south, or north, or whatever direction that happens to be. I think that actually is north. Let's see here. Yeah, because that would be towards Polaris, right? So to the north, I would say I see that smaller guy. So it can be useful to determine north as well. We're coming up on the end of this thing. I got to tell you, the viewership really started to climb at the end there, so I'm almost kind of sad to end it for the night, but I do appreciate all of you guys coming. Now that there's a lot more people, I'm going to reiterate. I'm going to bring up my visual aids here. There we go. I'm going to reiterate that I am the membership director for the Northeast Florida Astronomical Society. If you are interested in astronomy, if you are buying a telescope or have bought a telescope or want to learn more about buying a telescope, or not just telescope stuff, if you just want to learn more about the universe, come to our monthly meetings and learn all about space and talk to other cool people and just be a part of the astronomical community here in Jacksonville and support what we do and our education efforts, because we are a nonprofit organization. You can always go to nefas.org, membership, join NEFAS, and I'm just going to throw that in the chat real fast. nefas.org. And if you live in the St. Augustine area, there is a club down there as well, which I know some of the people in the group chat, I know for a fact, are in this club, and that is the Ancient City Astronomy Club. I happen to be a member of both, and you can do that too. They're another great group of guys. They have a great observing location on the St. Johns County Fairgrounds, and their website is ACAC St. Aug Florida, staugfl.org. It's a little more complicated. I'm just going to throw it in the chat for you guys as well. Highly encourage you guys who live in the area to join our astronomy clubs. If you are joining us from anywhere else in the world, because I have advertised this pretty far. So if you're joining us from not Northeast Florida and you are interested in astronomy, I encourage you to find a club near you. There's almost certainly an astronomy club by where you live. And you don't have to run right out necessarily and join, but look them up, because maybe they do outreach, right? Maybe they have a Facebook presence or a forum or something, and get involved. Get involved with your local astronomy community if you're really interested in this stuff. It's the best way to go about it. Hands down, is to get involved with an astronomy club and get into some of those outreach things and look at that. So that's it. I just want to leave you guys with that. Got a couple more minutes left. I really appreciate you guys joining me tonight. I think it's awesome that you guys want to learn about the universe and about the hobby and everything else we talked about tonight. And just like we did tonight, where I let your questions guide the discussion in your life, let curiosity be your guide. And I hope you guys have a wonderful evening.